let's begin. So last time we just ended with finishing up set theory, axiomatic set theory, and now we're moving on to actually covering material in the book. Now we're not actually starting topology yet. We're going to start at chapter 0, introduction, and what the author is trying to do in this chapter is really quick introduce you to notation that you may or may not have come across before, introduce you to basic math, basic assumptions that he's going to make from the book all from here on out, and give you a really high-level taste for what topology is. We'll do one basic proof that I think actually belongs in the subject of topology over here, but other than that, this is all pre-math stuff and just notation that a lot of it you'll already be familiar with, even if you don't remember that you're familiar with it. Trying to remember how far over I can go. All right, don't let me go past this line without moving the camera. Okay? That way when you go back and watch it, A, the camera's no longer in shape since we got rid of games. And B, I don't want to cut it off. Okay, so what is topology? First off, it's one of the three major fields of pure math. So we split pure math up, roughly speaking, into three fields. We split up into topology, algebra, and analysis. Analysis is things like calculus falls into the branch of analysis. Algebra is the one that you're already the most familiar with, algebras. And then topology is the third branch of pure maths. So pure maths is roughly split up into these three branches. If you did calculus, you have some experience with this. Your algebra gives you a lot of experience with this. You probably have very little experience with this. Geometry would come into this category. So geometry is the one in this category that you have some familiarization with. Now, topology, we're going to use it two ways. We use it to talk about a whole field of math, and then we're going to talk about an actual structure that's a topology. There's a similar notion, well, you haven't done it in algebra, but there's a similar thing in algebra. We use algebra to talk about a field of math, and then there's an actual idea of an algebra that exists. Can't think of another example off the top of my head that you would have come across, but just be aware that we're going to define what exactly a topology is later in this class. In the first chapter in the actual book, we'll start by defining exactly what topology is. But then there's topology referencing the entire field of math. This is referencing topology as a field of math. So what's some intuition for what topology is? One of the intuitions that you commonly hear given is that it's a less structured geometry, or they often word it a rubber sheet geometry. It's a geometry where if whatever object you have, imagine it was now made out of rubber, and no matter how you stretch, bend, and pull it, it's still the same object. So notice in math you're often interested in, is object A the same as object B in some sense? So in geometry that was congruent. Is triangle A congruent to triangle B? That's what you were interested in geometry, was a congruence relation. And what exactly did that mean? That meant that this side's the same long as that side's the same long as that side's the same long as that side, and all these angles are congruent. Using congruent again. All these angles measure the same somehow. That's what we meant for these two triangles are congruent. Well, in topology, when two things are the same, the word for the same in topology is called homeomorphic. If two things are homeomorphic or the same in topology, you imagine that whatever structure you're talking about was somehow made out of rubber, and you could stretch, pull, and bend it. And if I could take one object, stretch, pull, and bend it to create the other object, then they are the same. They're homeomorphic. They're the same in topology. So these two things are the same in topology. Any closed curve that you can think of would, in topology, be considered the same. Another way that we think about a topology is that it preserves proximity. Any points that were close to each other are still close to each other. Wow. So imagine I start out, when you think about it as a transformation. So if I think about this triangle here. Imagine that this is actually a rubber band, and it's made out of actual atoms, and this atom is next to this atom, and then I take it, stretch, rotate, pull, whatever I do to it, and I make it look like this. Notice that if this were made out of a rubber band, those atoms might end up right here and right here, but the two atoms that were next to each other are still next to each other. Any points that were close to each other are still close to each other. So while we don't preserve distances, and while we don't preserve lengths, distances, metrics, we do preserve proximity. That's what's preserved. Let me show you a bad topological transformation. Imagine I had this rubber band triangle, and I got this part of the rubber band really hot, this part of the rubber band really hot, and then I fused it together to make two loops in my rubber band. That is now bad, because this atom and this atom used to be not close, and now we made them close by making them actually touching there. That's bad. We did not preserve proximity. These two things are not the same topologically speaking. Does that make sense? The typical example that's given in topology as a three-dimensional example is that a coffee mug and a donut are topologically equivalent. If I had a coffee mug and it was made out of real stretchy material that I could deform, I could take that coffee mug and I could reform it into the shape of a donut without any rips or fusings together, keeping everything that was close still close.
How do you get the hole?
The coffee mug handle.
You can't do that.
Right? You have a coffee mug
Art class right here, baby.
with a handle coming out of it, right?
Yeah.
And then you turn that into a donut where the hole here would be the hole there. So you would slowly work all this mass up and around it to make it into a donut. They would be topologically equivalent.
Wouldn't you have to put the two sides together though?
No, because the coffee mug, I could flatten its edges down basically, and then squish it over.
Okay.
You could almost think about it like some surface with like jelly in there that I could squish around and reform around and put in a different spot. Then I could reform into a donut. So we'll work more and help establish more intuition for these types of things. It's not expected that you would see that right out the door and say, oh yeah, that makes perfect sense. This is meant to give you an example of, oh, that's weird. That's what it's supposed to trigger. But hopefully this one makes perfect sense, because that's a lot easier to see. So that's what a topology, loosely speaking, is. It's like it's one of the lightest structures you can give to a set to start giving it structure of some sort. So we'll take a set and then we'll give it a topology, which will be a structure on it. And now we have a notion of proximity or closeness. And that's what a topology gives you. So we're going to take some set and we're going to give it just a little bit of structure called a topology and see everything that we can start inferring, knowing about those sets just with that little bit of structure. And then we'll add more and more and more structure as we go along, and we'll eventually get to something like a metric space. You can start talking about distances like you're used to in geometry.
I have a question.
Yes?
So, with these sets, are we going to be dealing with the area of these objects?
You can't talk about area unless you have a metric.
And there isn't one in topology?
And a metric is something that you work up to. I think it's like chapter 5 of the book is metric spaces. So you'll work your way up to a metric. You don't have a metric to begin with. I don't know that we'll ever talk about area in this class, because that's an analysis concept. Because typically an area is defined in terms of an integral. Were you in calculus? Yeah, you were in calculus.
My brain wasn't, but my body was.
So in calculus, that's where you actually define what an area was. It was an integral. And we're not going to define an integral in this class, so I don't think we'll ever be talking about area. We may, I don't know. I don't remember the book that well. Remember, all I did is I went through this book once in college, and that's what I've done. So I hardly remember. I remember, like you remember calculus, except for you just took calculus. I took this like 4 years ago. So I'm not sure what we're going to cover, but we'll find out. I just know I liked it. So that's why I'm doing it again. Any other questions? Okay, moving on to some common sets. Hopefully we're all familiar with these. We've kind of narrowed down to more repeat students. So if there's one that you're not comfortable with, stop me. So first off, the empty set. You better be comfortable with this after we just did axiomatic set theory. I don't know if anything came up more than the empty set. And the empty set is inside every set, right, Rhoda? No, it's not even in the empty set. All right, and then we have the natural numbers. What are the natural numbers? I think for the purposes of this class, they include 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, etc. Exactly the way that we defined them in set theory disparately. That's what the natural numbers are. Z, what's this? Integers. Z with a plus up here.
Positive.
The positive integers. Is 0 in here?
No.
0, but it's even. What?
What?
Exactly. No, it's not in here.
Couldn't see it.
That was you in calculus. I remember that still.
Literally just laughing at us.
Z with the negative up there is the negative integers. Q is the
Rationals.
rationals. What are the rationals?
They can be divided. Or sorry, they can. Wait, they can be divided.
into a fraction.
It's all the numbers A over B, where A and B are integers, and B is
Not 0.
not 0. Wonderful. That's what the rationals are. All the fractions you can make is one way of saying it, right? And then we can do the same thing with Q. We can have Q to the plus or Q to the minus to mean all the positive rationals or all the negative rationals. R is
All the real numbers.
all the real numbers. What's a real number?
Everything including the empty set.
Anything that has an end.
Yeah, the real numbers are kind of hard for you to put just a definition on. And so, the intuition for what the real numbers are is, if you don't know what complex numbers are, then real numbers are every number you think of as a number. That's what a real number is. If you do know what complex numbers are, real numbers are complex numbers without the imaginary part.
Right.
So the real numbers are a subset of the complex numbers. And notice, the empty set is a subset of the naturals, is a subset of the integers, is a subset of the rationals, is a subset of the reals.
I thought you just said the empty set.
The
is
empty
not
set.
included in any set.
It's not.
Set isn't in
Then
the
how is
set,
it a
but
set?
It's not in every set. But a subset and is a member of a set are not the same thing. The empty set is a subset of the set containing one.
Right.
The empty set is not in the set containing
Right.
one necessarily.
Because everything in the empty set is in one.
Yeah, everything in here is in here, but this is not in there.
Right.
So the empty set is not in that set, but the empty set is a subset of that set. So it's true that the empty set is a subset of any set. It is not true that the empty set is in any set.
Okay.
Which, these two things, students get confused on left and right. So, gotta specify. Some more assumptions that the author is going to make here. For those of you who haven't done calculus, he's going to assume that you can do all the algebra that you're used to with the real numbers. For those of you who have done calculus, we're going to assume the field axioms, the positivity axioms, and the completeness axiom. Actually, for those of you who did geometry, you should at least know this one, the completeness axiom. But so these are properties on the real numbers. For example, addition on the real numbers is commutative. That's one of the things we're going to assume. Multiplication on the real numbers is commutative, and you can distribute the way you think you can distribute. There's negative and positive numbers, just like you think of negative and positive numbers. All that. So we're just going to assume all these properties on the real numbers. We're not going to prove these things out. Why aren't we proving these things out if we're going to use them? Because working with these things and proving with these things falls into the field of analysis. It's not part of topology to do proofs using these things. We're mostly going to use the real numbers from here on out for examples to help establish your intuition. Make sense? So if you want to rigorously look at the assumptions we make on the real numbers, the axioms on the real numbers, and you want to prove things like there's one and only one number 1 in the real numbers, or 1 and only 0 in the real numbers, then that would be some stuff that you do at the beginning of calculus class. Or you might even do that in an algebra class. But not in topology. So we're going to assume some things in our examples, mostly for the sake of our examples, to help give you intuition with stuff that you're already familiar with. Okay, so any questions there? In other words, I might use plus, multiply, divide, stuff like that, stuff that you're already familiar with, but we're not going to prove or give it explicit definitions. Okay, interval notation. Make sure we all understand interval notation, because this gets real confusing for students because we use a comma b in parentheses in many different ways. Sometimes we use this as an ordered pair, sometimes we use this as an interval, sometimes we use it, well, I can't think of another case off the top of my head. Anyways, we use parentheses in a lot of different ways. One of the ways that we can use it is for what we call interval notation. So if I have a and b, where a is less than b, these are both real numbers. You understand what I mean by that? So we have two real numbers, a and b, where a is less than b. Then when I do open parenthesis, a comma b, close parenthesis, and I'm using this, I'm talking about an interval or a set. What does this mean? This means a set of all x between a and b.
Like a line segment.
It's just like a line segment, not including the endpoints. So if we draw the real number line right here, and here's a on the real number line, and here's b on the real number line, then this interval AB is all the points in between a and b, not including a, not including b. Does that make sense? Nothing weird there? And then, if you understand this one, the rest of these almost just follow trivially. If we use close brackets AB, then that means all the x between a and b, including a and b. Right?
Yeah.
And then, if we have a close bracket on this side, open bracket on this side, that's all the x between a and b, only including a. This is all the x between a and b, only including b. What about this one? A to infinity.
From that point to the positive direction.
Yeah, it's just all the numbers bigger than a. That's all the x bigger than a. And the way that we've seen this on number lines is they typically do something like,
Arrow.
they put a here, they do an open circle at a, and then they draw a solid line pointing that way. All the points starting at a going that way. All the numbers greater than a. Similarly, all the numbers greater than a, including a. Alright, what about negative infinity to b?
All the numbers smaller than b.
That's going to be all the numbers less than b. Negative infinity to b, close bracket. That's all the numbers less than or equal to b. Negative infinity to infinity. That's all the real numbers. Right?
Yeah.
And then, if it's just a in close brackets, then it's just a set containing a. It's a one element set.
So these are all sets.
Oh, and we missed one, right? What about a comma a like that?
The empty set?
You can call it the empty set. It doesn't make sense though. There are all the numbers greater than a but less than a.
No.
Doesn't make sense. Alright. These intervals, a to b, negative infinity to b, a to infinity, negative infinity to infinity, we call open intervals. These intervals, a to b, negative infinity to b included, a included to infinity, and a to a, we call closed intervals. And then these two we call half open. It's just names. We'll see why we use these names once we get to like chapter 2, I think.
Why do you call those two half open and not the infinity one? That's what I was wondering too.
Why do, oh, so you want to say this is closed,
Half closed.
or this one should be half closed, and I think also this is closed. We won't put it on there because we don't want confusion. So you will have a perfect understanding of why exactly we call these things closed and these things open by the start of chapter 2, I believe, in the book.
That's a good word.
It has to do with the fact that these are closed sets in the standard topology on the real number, and these are open sets in the standard topology on the real numbers. Okay? So that's where they get their open and their closed names. But for now, this is just what they are. I don't know a way to establish good intuition for it. I guess here's one way you can think about it. All the inequality signs in this, and this are less than or greater than, and all the inequality signs in this, and this are less than or equal or greater than or equal. And then these two include one of each. Maybe that's intuition. Does that make sense what I just said? Okay, so I don't know. I'm just finding patterns. I don't know a better intuition to give you than that. Okay, now let's get to some dense notation. Let D be a set, and assume that for every element in D, for all little d and big D, there exists a set S sub D. Alright? So if big D has 10 elements, then there are 10 S sub Ds. You with me so far? So let D be a set, and assume that for every element in D, there exists some set S sub D, S sub little d. Let C be the collection of all the sets S sub little d. Then C is called an index collection of sets, and big D is called the indexing set. So if big D has 5 elements in it, how many elements does C have?
At least 5.
5. Exactly 5. It has one set for every element in D.
Oh.
Make sense?
Yeah.
For every little d and big D, we have a set S sub little d.
Right.
C is a collection of all those S sub little d's. If that's the case, then we call C an index collection of sets, and we call D the indexing set.
Right.
We denote the collection C by the set of S sub D for each little d and big D. That's how I'm going to read that. Now, this might seem like weird notation to you, and that's why we're introducing it early on, because then it's going to come up again and again in the book. Basically, everything we cover here, when it comes up again in the book, from chapter 1 on, we'll reintroduce it. But it's just, get you comfortable with all the notation now, that way when we come across it later, you've at least seen it once.
Read it again.
Yeah.
The S, D, D, in D.
Alright. You're saying starting here?
No, well, yeah, go ahead. Start there. I was just saying. Start.
We denote the collection C. What's C? It's the set of all sets S sub D.
Right.
Take all the S sub D's, put them in a set, that's what C is. And there's one S sub D for every little d and big D.
Right. Why is there another D right there, though? Like in your notation. What is that other D outside the parentheses? Yeah, what does that represent?
Yeah.
Okay. We denote the collection C by the set of all S sub little d for each little d in big D.
Okay. So each element in the set.
We'll see a few examples
Right,
of this to
because
help you
little d
comfortable.
is just an element in.
Little d is just an element in big D,
Okay, yeah, I totally understand.
right? Or we just write S sub D, no indexing set here, when the indexing set is clear from context.
Right, okay.
So if it's obvious from context what set we're indexing with respect to, we'll just write it this way, otherwise we'll write it this way. We'll come back to this definition after we look at some examples. Okay, let T be the set of all towns in Arizona. Good so far? And for each town in all the towns in Arizona, let B sub T denote the set of all barbers who run a business in town, little t.
What's a barber? Somebody who puts up barbed wire fences.
Barbers.
Someone
That's
cuts
their
it.
sheet.
Okay, I'm not listening. We're just in Arizona and they're everywhere, so.
I get you.
And town, like you barber.
I get you. Okay. So T, so then what is T?
It's a set of
It's a
all
set of all the
barbers
towns
in all
in
the
Arizona.
towns.
It's a set of all the towns in Arizona.
Yep.
T is equal to set of all towns.
Oh, right. I say T.
So we have Colorado City in there, we have Centennial Park in there, we have Phoenix in there, we have Tucson in there.
Town, come on.
Town, city, whatever. Alright, now B sub little t denotes the set of barbers who run a business in town little t. So if little t is Phoenix, then B sub Phoenix is the set of all barbers who run a business in Phoenix.
Right.
Right?
Right.
So what is B sub t for all t and big T?
It's all the barbers in a certain town.
In one element of all the towns.
In all the towns.
It is the set of sets of barbers. No. So it's going to be a set like this. B sub Phoenix, comma, B sub Flagstaff, comma, B sub Colorado City, comma, etc., etc. It's the set of all the sets of barbers who run a business in that town,
In separate towns, yes.
in each separate town. So B sub Phoenix is all the barbers who run a business in Phoenix. B sub Flagstaff is all the barbers who run a business in Flagstaff. Notice a barber could be in this set and in this set, right? Notice this set could be empty. There could be no barbers in that town.
You can't have two barbers in two towns.
Can I have
Yes,
a?
it can.
Can you run a business?
Okay.
Can you run a business in both Phoenix and Flagstaff?
Same people. Yes, I see.
Okay. So now let's do an even more concrete example in case you're still not getting it. Let's say that T is equal to the set of towns X, Y, and Z.
Okay.
Alright? These are the only 3 towns in all of Arizona. And let's say that the only people who run a barber business in town X is Bob and Frank. And the only barbers who run a business in town Y is Jack and Matt. And the only barbers who run a business in town Z is Bob and Jack. Then what is the collection B sub T for all T and big T? What is this?
Bob, Frank,
What's the first thing I write here?
a set.
Bob?
No, right, a set.
Yeah.
A set?
Right, the start of the set.
Oh, you're right. Set Bob and Frank, and then set.
Perfect. The set containing Bob and Frank. And then we do
Jack and Matt.
Jack and Matt.
the set containing Jack and Matt. And I think from here on out you get how it works. So now let's go back to the definition and try and power this thing home. Let D be a set and assume that for each little d and big D, there exists a set S sub D. In our example, big D was all the towns. Little d would have been a town like Phoenix. And S sub D would have been all the barbers who work in a particular town, little d. Good so far? Let C be the collection of all S sub D sets. So in our example, this is C.
Yep.
Then C is called an index collection of sets, and D is called the indexing set. Notice in here, we're going to have one set for every element in T. We're going to have B sub X, comma, B sub Y, comma, B sub Z. Right? So, then C is called an index collection of sets, and D is called the indexing set. And then, again, we denote the collection C by the set of all S sub D for each little d and big D, or just the set of all S sub D when it's obvious from context what big D is, where this little d comes from. One more note, sometimes we don't care what the indexing set is, and so we'll also just use this notation, where D comes from some indexing set, but we just don't care what it is. You'll be used to that by the time we get to it. Maybe I shouldn't have even said that. Continuing. Alright, so we go with the definition. You feel like you got it? It's a little bit dense, but once you understand the notation, there's no regressing. It's like, once it makes sense, it makes sense. Okay, so we've gone over all the examples. Special cases. When the indexing set is consecutive positive integers, what are consecutive integers?
Right by each other.
The two
No.
atoms.
What?
The two atoms.
Two atoms. They have to be in order, sequential order.
Yeah, they have to be in order. So consecutive integers is like 3, 4, 5, not 3, 6, 9. 3, 4, 5, 6, 7, 8, 9 are all consecutive integers. Okay? So, when the indexing set is consecutive positive integers, in other words, you can write D as, starting at some positive integer m, then it's just m, m plus 1, m plus 2, m plus 3, m plus 4, until some integer n. All consecutive integers. Good so far with consecutive positive integers? Then, instead of writing the set of all S of D where little d is in big D, we instead can write the set for all S of D where D starts at m and ends at n. This is very similar to how you've seen sigma notation.
Right.
Sigma notation, we sum up all the k's starting at some index, ending at some index. Right?
Yeah.
You've all seen something like the sum from k equals 5 to 17 of k squared plus 3.
Yeah.
We plug in 5, that gives us something. We plug in 6, that gives us something. So we keep plugging in consecutive integers starting at 5, ending at 17. And we always use, not always, but as a general rule, both these numbers are positive integers. That's exactly what we're talking about here, except for we're listing out sets instead of adding up numbers, but same idea. So if you think, why would we ever use this? The same reason we use that sigma notation.
So like we'd say stop at past Phoenix or whatever.
Well, that was only for towns, but it's very common that our indexing set is natural numbers.
Okay. How come it's not n plus 1 in the set big D?
It really should be n plus n.
We end at n.
Which should be
Well,
n
you say
plus n,
consecutive
right?
positive integers, don't integers go on forever?
Yeah, this is our ending integer.
She's done.
So this could be 5, this could be 17. Then we're saying 5, 6, 7, 8, all the way to 17. Notice this could be 5 and this could also be 5. In that case, it's just 5. This just helps you understand the pattern to get from m to n. Keep incrementing by 1.
Seems like the D and the M would be switched then. Because
You're
if
saying
you're
here?
starting at M,
For all little d starting at m till n. Same thing with our sigma notation. If I do, it's the sum from all d equal to m until n of d squared, something like that.
okay.
So it's that exact same convention. In fact, it is not uncommon to
It
see
looks like an
sigma written
equation.
this exact way. This is a common way you'll see it. Sigma from, we'll use d equal to 5 to 17 of d squared. This is notation that's used a lot of the time, instead of putting them down here and up here.
Okay. Wait, it kind of looks like an equation.
They kind of look like an equation.
That's where That's what,
Oh, you're viewing this as an equation?
yeah. Like
Yeah.
it's all equal to n, but the way you read it is
Yeah.
small, high.
When you see it in context, because we have this just by itself.
Right.
Well, I see what you're saying. Yeah, it's not an equation. And maybe I could do better to like center the n above it so it's not so on one side so you don't think it's an exponent or something weird. I don't know what you think it was, but yeah. Okay, so let's see an example where we might use an index set. So I can say D is the numbers 15 through 25. The actual numbers 15 through 25. And I can define each S sub little d as a set of all the people in here whose age is D. Then I'm creating a set of people for each number here. So S sub 15 would be all the people in here whose age is 15. S sub 16 would be all the people whose age is 16. And we can do that all the way up to 25. Huh?
B25.
Anyways.
Robert's 25.
Forget my
Yeah, just think about William.
Donnie's like
Robert.
20.
Robert's the one because we talked about in Sunday school.
Okay. Anyways, so another way that we could write this, S sub D from D equal to 15 to 25 would be S sub 15, the set of everyone in here who's 15, the set of everyone who in here who's 16, all the way up to the set of everyone in here who's 25. Right?
I know I'm getting confused with when we start using this.
Yeah, it's dense notation. That's why we're introducing it now, and then you're going to see it in proofs down the road. And we're going to do a proof today. It's a real easy proof, as in the idea behind it is very easy, but it has dense notation, so you're going to get lost in it. But the idea is pretty simple. And it's going to be just trying to hammer home. Well, no, actually, we use that proof a lot, so it's not just to hammer home the notation, but it helps. Anyways, we go with this example using this notation is the same as this. You understand what both these sets are talking about? It's the set of people with that particular age.
Yeah.
Okay. Collection of sets, S sub D from D equal to M to N. Notice M and N are going to be positive integers where N is greater than or equal to M. With me so far? So this set is said to be nested, provided that the next set in here is a subset of the previous one. In other words, if I said that this set was everyone whose age was greater than 15, and this is everyone whose age is greater than 16, and 17, and 18, and 19, and 20, this would be nested. Right? Because everyone whose age is greater than 25 also has their age greater than 15. So S sub 25 would be a subset of this. S sub 24 would be a subset of this. In other words, the next set is always a subset of the previous one.
Okay.
Or the current set is always a superset of the next one. I don't know if we've used that terminology before, superset. But it's terminology. So we'll stick with the subset one. The next set is a subset of the current set. That's what it means to be nested. So let's look at an example of a nested collection, other than the one I just said. Okay, the collection of sets, negative 1 over n to 1 over n, where n is a positive integer, is nested. In other words, let D be the set of all positive integers, and let S sub little d be all the numbers from negative 1 over d to 1 over d. Then,
You made a B.
S sub little d for all d and big D, thank you, that's a little d. Then S sub little d for all little d and big D is nested. Let's help hammer this home. What's S sub 1?
Negative 1.
It's negative 1 to 1. It's this set.
Right.
It's all the real numbers between negative 1 and 1, including negative 1 and 1.
Right.
Is 1/2 in there?
Yes.
Yeah.
Oh, not in there, but yeah. But yeah, no, not in there.
Yes, it is. This is
Oh.
a set.
Yeah.
This is a set of numbers.
I was waiting for you to say 2.
Is 0 in there?
Yes.
Is 1 in there?
Yes.
Is the square root of 2 in there?
Yes. Oh,
Yeah.
yes. Correct.
Is,
No, it's not.
Is the square root of 2 bigger than the square root of 1?
Yes.
And what's the square root of 1?
1.
1. So that's the biggest thing in there. Anything bigger than that's not in there, including the square root of 2. Is pi in there?
No.
Is negative 3/4 in there?
Yes.
What about positive 4/3?
No.
Okay, I think you've got this. Alright. It's the set of all the numbers from -1 to 1, including -1 and 1. Alright, what's S sub 2?
1/2 and -1/2.
It's all the real numbers from -1/2 to 1/2. Is 0 in there?
Yes.
3/4?
No.
11/27?
No.
Yes.
Alright, I think you understand what that set is. Is there anything in this set that's not in this set?
The empty set.
There's nothing in there that's not in here. Is there something in here that's not in here?
Yes.
Okay, so this is a subset of this.
Yes.
Good? What's S sub 3? I guess I had 2 more.
Negative 1/3
Negative 1/3 to 1/3. S sub 4. How many elements are in here?
Taken out.
Infinity.
Infinite.
And pi.
There's infinitely many. One for every positive integer. I can map 1 to something, 2 to something, 3 to something, 10,564 to something, etc. Okay.
Pretty small.
Now notice that this is a subset of this, is a subset of this, is a subset of this. The next element is always a subset of the current element. Or the previous element, if you want to say that. Let's set up one more nested set. Let's pretend that S sub B was equal to 1, 1, that set. What's S sub 1 equal to?
1.
Oh, sorry, negative 1 to 1.
Huh.
What's S sub B equal to? Or is S sub 1 equal to? Negative 1 to 1. What's S sub 2 equal to?
-1/1.
Negative 1 to 1. What's S sub 3 equal to?
-1/1.
Not using this anymore. I'm not saying S sub D is equal to this. New example. Pretend S sub D is equal to this.
Right.
Notice no matter what D is, S sub D is always the same thing. This is in no way dependent on D. It's the same thing as when I give you a function. If I say f of x is equal to 2, what's f of 37 equal to?
2.
Okay.
Same concept, right? It's just a constant set. Question, would the collection then, S of D, would that be nested?
Yeah, everything's subset.
Yes. This set is always a subset of itself.
Um,
Okay, so there's like the one corner case with nested sets. If you just have the same set every time, it's still nested.
Probably help 2%.
What's that? You're good?
Yeah.
Oh, we haven't gone past the line yet. Okay. Good with nested sets? Any questions about nested sets?
Why nested?
Because they're always inside each other.
Is that what a nest does?
Nested, like, what do they call them? Russian nesting dolls. There's always a smaller doll inside. Not always, it eventually caps out, but honestly, it's not infinite.
Cool, I think I've done that. I don't know.
So this set is nested inside this set is nested inside this set is nested inside this set, etc. Okay, so good with nested. Any more questions about nested sets? Ready to move on? Okay, some definitions that you are already familiar with, especially since we just finished set theory, but we'll go over them anyways, and we'll go over them, the definitions that we'll use in this class from here on out, or at least how the book will define it. So we already know what U union V is, right?
Yeah.
In this class, we're going to call it the set of all X such that X is in U or X is in V.
You said that last time.
Not quite. Look at this. The set of all X such that. We didn't say the set of all X in something such that. Right?
Right.
So it's that dangerous notation that if you're not careful with it, you could end up talking about sets trying to talk about sets that aren't actually sets. Right? So it's going to be given to you where these come from. I mean, we know what X is in. What's X in?
The rails. Or
X is in union of U comma V. Okay, we can say it's in that. Right? So we can say some set that's in and then define this real easy. So no, this wasn't the exact definition that we used last time. You could use the definition that we used last time and you'd be fine. But from here on out, we're just going to use this definition because it's simpler and it helps us do easy proofs just using logic real quick. Those of you who have already been doing proofs with union, for example, like proving that union is associative, you use the fact that or is associative to prove it, right? With this definition, that becomes real easy. Similarly, with the intersection, it's a set of all X such that X is in U and X is in V. Nothing weird there. Here's the notation that might be weird for you. We're going to union on UD for all little d and big D. That is equal to the set of all X where there is some UD in the collection such that X is in that UD. The way that we've been writing that in set theory is this. The union on the set is the same thing as the union on everything in the collection of sets for every object in the indexing set.
If you union everything in the set, isn't it just D? 'Cause I can just put it down.
No, U sub D. So D could be the numbers 15 through 25. U sub 15 could be everyone whose age is 15. And U sub 16 could be everyone whose age is 16.
why are we using
So the union on this is going to be all the people we're talking about, where D was a set of numbers. You see how that's drastically different? It's just exactly how we've been using the union like this. When you did the union on the set, what was that? That was the set of all the elements of the elements. So we've already seen this in axiomatic set theory. Review this notation. This is using the exact same notation. Or not the exact same notation, but this is the exact same idea.
Do you have an example of that one?
I didn't write one because I thought since it was just in set theory we'd remember, but we can write one real quick. Oh, let's just use one of our examples here. So bx, dy, bz. Then if I want to do the union for all t in T of b sub t, then that would equal log Frank Jack math.
Right, I now understand. Okay, right.
Right? It's the same thing as the union on b sub x, b sub y, b sub z. The way that we defined this in set theory. The union of a set is the set of all the elements of the elements. Take all the elements of this, and all the elements of this, and all the elements of this, and put them down here. That's what the union on this set is, or that's what the union of all the BTs for each little t and big T is. Think you got it?
What you did was you used a U, so it was so confusing.
Sorry. Yeah. We're going to be using U's for open sets a lot, so you need to get comfortable with seeing the unions of your U's, because the standard notation is used U for open sets. And that's the majority of what you talk about in topology is open sets. So, let's read this one more time, because this is where the heart of it is. The union of all u sub little d for every little d of big D is equal to the set of all x where there exists a UD in the collection of UDs containing x.
Perfect.
If x is in one of those UDs in the set of UDs, then x is in their union. Does that make sense? So if I know that x is in the union of all my UDs, I know that there is some u sub d such that x is in there. If I know that Bob is in this union, then I know that there is some b sub t, namely b sub x, such that Bob is in it. Does that make sense?
Yeah.
Because that's the back and forth we're going to be going through a lot. We're going to say, since x is in this, then there exists some u sub d such that x is in that.
Right.
That's going to be a logical leap that we make a lot without any further explanation. Make sense? Okay. And then, if you understand the union, the intersection is almost identical. The intersection of all u sub little d for all little d and big D is the set of all x, where for every UD, x is in it. X has to be in all the UDs in order for it to be in the intersection of all of them.
So if
What
you
would
had
it-
Bob with y, then it would only be Bob, right?
Yeah, so if t was only x and z, then the intersection, then switching this to an intersection, will give us just Bob.
Okay.
But with it as it is, then the intersection would be just the empty set. Does that make sense?
Yeah.
Okay. Put that back so we don't have anything weird on the board. So, oh, we didn't start with the intersection here. Oh yeah, we covered that. Okay, so those are the 4 definitions. Maybe just ask if there's any questions you have on any of those.
Really like it.
And once again, our intersection is defined so that the same way that we define the intersection on a set in set theory, it's the same thing as this. Good? Ready to move forward? Move my camera. And try and get as much whiteboard as I can. Okay. Moving on to this one. Oh, well, now I think no, we'll do it. All right, so going back to our previous example where T is the set of all towns in Arizona, and let B sub T be the set of all barbers who run businesses in town T, then what would this represent?
Every person, or every barber in
All the barbers.
all the barbers. in
All the
Arizona.
barbers in any of the towns. It's the set of all barbers who run a business in any town in Arizona.
Yeah. And then this next one.
And what would this one be?
All the barbers.
No, a barber.
Barber that runs-
Barbers that are in every town.
This is a set of barbers who run a business in every town in Arizona.
Yeah.
The set of barbers who run a business in any town in Arizona, or at least one town in Arizona. This is a set of barbers who run a business in every town in Arizona. Good?
Yeah.
Okay. Let's do a more concrete example. For each little r in the positive real numbers, let u sub little r be the closed interval negative r to r. You with me so far? Okay. What would the union of all those sets be for every r in the positive real numbers?
It'd be R to R.
Everything in that set.
It'd be just a set.
The
over
average
yeah.
between negative R and R.
It's a bounded set.
Well, that's what one of these are. But now we're going to plug in every real number, and we're going to union it up. So I'm going to take everything from negative pi to pi. I'm going to take everything from negative 100 to 100. I'm going to union up
So it's just
infinity to infinity for all real numbers. Perfect.
Oh, for each. That's what I was kind of missing.
Okay.
good?
Okay.
This is a set of all real numbers that show up in at least one of those intervals. Right? What about this? What does this equal?
The set of all real numbers that show up in every one of those intervals.
The empty set. Nothing shows up in all of these, right?
Yeah.
At this point.
Wait, I have a number.
The set containing 0 would be in all of them. And that's the only number in all of them. How do you get from a negative number to a positive number and not include 0? You don't.
Yeah, you're right. So it's not the empty set.
I know I'm right. That's why I put it. It's like take 0 there.
Oh, yeah. No.
Yep, that's why I did it. Alright. Feel like you understand that example? Getting comfortable with the notation? No questions still? Huh?
I said starting to get comfortable.
Starting to get comfortable. Alright. I'll take it. Once again, when the indexing set D is these consecutive positive integers again, we're going to introduce some more notation. Then the union for all little d and big D of S of D is just going to be the union for all S of little d starting at D equal to M and going to D equal to N. Notice how this notation compares with,
You erased it.
I erased the one spot I need a reference again. Oh, that's terrible. But it's just like we had the notation, the set of all SD, D equal to M from M to N. A concrete example was when we made this 15, this 25, and we said each S of D was all the people whose age is at least 15, at least 16, at least 17, etc., all the way up to 25. So, similar notation. The union of all S of little d starting at D equal to M and ending at D equal to N. You good? And we have similar notation for the intersection. So when the indexing set is consecutive positive integers from M to N, then the union of all the sets we can write this way, and the intersection of all the sets we can write this way. Any questions? Keep going.
Yeah.
What?
Were we doing that up there? Oh, we're just changing our notation.
It's
We're
just
changing
more
our
notation.
Yes. I was
For-
like, we're not
A special case.
changing anything.
It's just right there.
Okay. Another definition, one that we're already comfortable with, but we'll go over it again. Let A and B be sets. If the intersection of A and B is the empty set, then what do we call A and B?
Disjoint.
Disjoint. Then A and B are said to be disjoint. If I have a collection of sets, and the intersection of any two sets in there is empty, we call the whole collection pairwise disjoint, or in this class, mutually disjoint. Same thing though.
If you what?
If you wada, then you're probably a duck. All right. Okay. So we have A and B are sets. If their intersection is the empty set, then A and B are said to be disjoint. You're good with that, right?
Yes.
Let the set S of B, so this is a set of sets, be a collection of sets. So here's some collection of sets. If any two sets in SD, the set containing SD, the set of sets, if any two sets in this collection of sets are disjoint, I wrote that weird.
Isn't it all of the sets?
If for any two sets in SD you grab, then they're disjoint. Then the collection, the entire collection, is said to be mutually disjoint.
Okay.
So none of them, so if all of them are disjoint then.
So for all x, for all y, let's just say it this way.
Where you take the union.
For all x, y in SD, grab any two sets in there. The intersection of x and y is equal to the empty set.
Yeah.
Mhm.
For any two sets in this collection of sets, their intersection is the empty
That's
set.
saying the first thing.
That's, no,
It's saying disjoint.
I don't know.
No,
two
it's
sets are disjoint if their intersection is empty.
No, because
A collection of sets is mutually disjoint if for any two sets in there,
Mutually, like.
they're disjoint.
For any, but not
But
for
it's the same thing.
every.
Yeah.
Pick two sets in there. Any two you want. X, Y. Is their intersection always the empty set?
Yeah.
Then it's mutually disjoint.
Well, if everyone still mutually disjoint, of course, yes. Okay.
It is for everyone.
What's up?
For any and for every are two identical verbiages for this symbol. For every, for any, for all. They're all logically equivalent.
Okay, that helped me because I say for any, like you can pick
Yeah, you kind of change your terminology based off of
context.
what helps it flow with the English that you're using.
Right.
But yeah, so this makes sense now?
Yeah, so for every, yes.
For every, for, the English sounds weird, but yeah. For every combination of two sets you can take out of there, their intersection has to be empty for it to be mutually disjoint.
Right, okay, thank you.
Okay, and now, let's go over the intuition for what's called the union lemma, and then we'll do the proof. Maybe we'll read the proof, go over the intuition, or read what we're trying to prove, go over the intuition, then go over the actual proof.
Okay.
So what are we trying to show? So let X be a set, and let C be a collection of subsets of X.
Right, like we've done.
Good so far?
Yeah.
Assume that for every element of big X, there exists some subset in C containing that X.
Mhm.
Or assume that for all X in big X, there exists some A sub X in C such that X is in A sub X. Let's go back to what I said the first time, maybe that helps more. Assume that for every element in X, there exists some subset in C such that X is in that subset.
I'm sorry, but okay, that's like what we've been doing over here.
Not necessarily, but all we're saying is that for every element you can grab in X, there is a set in C that contains that element.
No, there's a set in C. There's a set that is a subset of C.
Not a
No,
subset of
there's
C.
a set
In
C that contains an element. Yes.
Yes, C is a collection of subsets
Right.
of big X.
Right.
That's what it is.
Right.
Okay. Then the union of all the subsets in C is equal to X.
Of course.
It's a very obvious theorem to introduce you to the notation. So let's go over a picture of what we're saying here. So here's big X. We're saying if for any little x in big X you can find, pick any one you want. If for any one you pick, you happen to pick this one, there exists some A sub X that contains it, then the union of all the A sub X's is just going to be X.
Right.
Does that feel obvious, what I'm saying?
Isn't what I was trying to say, but you said it wrong though.
If I said you were wrong, then you said it somehow different. Because this is right, and I'm never wrong. I don't know what you were saying. Okay, so let's do the proof of this. So notice, sorry for those of you who are used to me writing as the first line of my proofs. Assume all the antecedent to our proof. I'm not going to write that here. So, starting at line 1, I'm going to assume that we have some set X, and I'm going to assume that C is a collection of subsets of X, and I'm going to assume that for every little x in big X, there exists some a sub x in C such that x is in that subset. What am I proving? I'm proving that these two sets are equal. How do we prove two sets are equal?
They're subsets of each other.
That everything,
That they're subsets of each other. How do I show that this is a subset of this?
everything in that set is in the other set.
Right. Grab an arbitrary element out of here, show it's in here. Therefore, everything in here is in here. And then do the inverse to show this is a subset of this, therefore they're equal. Alright, so let's get to it. So let little a be some element in the union of these sets. So grab something that's in the union of all these sets. Now, since A is in the union of all these sets, that means that there must exist some x prime in X such that A is in A sub x prime.
When you say A is in the union of all these X.
So, since I know that A is in the union of all these subsets.
Okay, when you say A is in the union of all these subsets, you're not saying A is in every subset, you're just saying
No,
A
it's in
is
the
just
union.
somewhere.
Union of all together, you have a set.
Right.
A's in there.
Okay, so it's just an X.
Well, we need to prove that. You
Right.
can't just say it.
Okay.
Right? So A is in the union of all these sets, therefore A is in one of those sets.
Yes.
So, therefore, there is some x prime, who knows, in X, such that A is in the subset including that element.
Yes.
Okay.
Good so far?
Yeah.
Okay. Now, since by definition, A sub x prime is a subset of X,
Right.
Right.
remember, A sub x prime is in C is a collection of subsets of X.
Right.
So C is a collection of subsets of X, A sub x prime is something in C, therefore it's a subset of X. So since A sub x is a subset of X is given, then A is in X. Everything in here is in here. Since A was in there, A is in there.
Mhm.
Therefore, the union of all the subsets is a subset of X.
Because you grabbed an arbitrary A.
Yeah, we grabbed an arbitrary element out of here and showed that it's in here. Makes sense why that is sufficient for showing it's a subset?
Mm-hmm.
Okay, so now let's do the inverse. Let's grab something out of here until it's in here. Let little a be in big X now. Now we know that for every element in big X, there exists some subset in C such that that element is in that subset.
Right.
So let A in X, then I know that there must exist some A sub little a in C such that little a is in that subset.
Oh, there you go.
Yeah. Then, since the subset is a subset of the union of all the subsets, then A is in the union. Therefore, the union of all the subsets is a subset of big X. Therefore, the union of all the subsets is equal to X.
That was the most obvious thing I've ever seen.
Very simple, very obvious proof. We're going to use it 100 times in this class from here on out. Probably the most referenced proof in the class. It's very simple, very obvious, very straightforward. It just gives you a bunch of this notation. So if you were to just go grab some kid off the street and show them this, they say, oh wow, that looks complex, right?
Mm-hmm.
Because the notation's dense. So that's why it's a good one to hammer home.
Notation is so dense. This is pissing me off, honestly. Because I just keep going, but really it's like saying the most simple things I've ever seen.
It's just like when we first started logic. Remember using all the quantifiers in logic, and you had to read the sentence 10 times to finally understand it. Similar thing here. It's too hard to keep using English to say what you're trying to say, and you just gotta get comfortable with the dense notation.
Right.
And we like that dense notation, because then it says a lot in a little bit of notation.
Yeah, I love all of our.
So we love dense notation, and we want more of it.
We just hate learning it.
Well, it's a struggle, but we like it. Okay. So let's use this proof now let's use this lemma to do a quick proof. Not really a proof, but you'll obviously see it. So now, let C equal the set of all closed intervals from n to n plus 1 for every integer n. So this is negative 100 to negative 99. It's 0 to 1. It's 10,000 to 10,001.
It's the set of all those.
It's the set of all those closed intervals.
So I need to get out of my head that we're dealing with line segments, because that's what I keep thinking.
You can think about that as a line segment if you want.
But you don't think of that as a whole bunch of sets,
It's
at least I don't.
The set of line segments.
Right.
Sure. So let C equal the set of closed sets, or closed intervals, from n to n plus 1 for every integer n. Observe that for all x in R, then there is some n in Z such that x is in there.
Okay.
Right? Good, James? Okay. Therefore, the union of all these things is equal to what?
The integers.
Is it not C?
What is C? C is the set of all the intervals here.
C.
So you're saying the union of C is equal to C?
Yeah, no, the union of n and
Okay, this is also equal to the union of C, yes, but I'm wondering what does the union of C equal?
Oh,
the integers.
the rations.
The integers, the rationals. We're going to say every set with the right one.
All real numbers.
The reals!
Oh.
Yeah, that was just
The
a
reals.
guess.
Sorry.
Alright, because we're dealing with
Yeah.
line segments.
Not because we're dealing with the line segments, because we know that for all x in R, there is a subset in C containing it. Therefore, the union of the subsets is R. That's what this just proved.
Okay, you got it. Really.
Yeah, see, straightforward proof, and then you go to use it, and when you go to use it, this is going to happen 100 times in this class. We're going to make the leap over, I'm going to make the leap, and then the union of all these sets is just a set, and you're going to think in your head, how? And it's going to be that I keep using this straightforward, obvious thing that for some reason, when you go to use it in context, because I know, I read the author's proof, he says that the union of these is this. I'm like, how? Oh, yeah. Always gets me. So, let's go over what this said one more time. If X is a set and C is a collection of subsets of X, and for every element in X there exists some subset in C containing that element, then the union of those subsets is just the set
Why
X.
do we have this middleman subset? It's a middleman. This A of X. It's like, why can't we just say, if you literally go,
Here's where it's going to be useful. I've got some set here, and I'm trying to show that it's equal to some given set that I know. And the way I'm going to do that is I'm going to come up with some process, some procedure, so that for any element in here, I have S here, and I know that S is equal to the union of a bunch of sets here. You union all those up, and that gives you S. If I can come up with some procedure where for every point in here, I know how to assign it to one of these subsets, and I can find the subset that I can put that thing in, then these two things are equal. This thing which I just know is a union of these sets, and then this thing is a particular set that I'm trying to show is actually the same thing. I come up with some procedure for assigning each point in here to a subset that contains it, that's one of these subsets. And that's what makes me equal. So it's an extremely useful lemma. We're going to use it tons. And you can't cut out any middleman. I don't know what the middleman is in your reference.
the subsets. The A of X. That's the middleman.
The A of X. We're identifying a set. Instead of identifying it from knowing all its points, we're identifying it from knowing a bunch of subsets that contain all its points.
Right. See the middleman there?
It seems weird, I know, but as soon as we start using it, you'll see immediately the obvious applications. Here's kind of a contrived example just to get you comfortable with
Okay,
it.
so let's go over this one again.
Okay, let's go over this one again. So, for all x in big X,
Okay.
there exists an a sub x in C such that x is in that a sub x.
This.
Therefore, the union of all these a sub x's is big X. Is it clicking?
Yeah,
That one clicked for me.
especially when you drew
When you
it
don't.
out and
I thought I heard it. No.
pictures.
And maybe that's because you just all said yeah. No,
No, you heard your pen click.
Yeah.
That's what I thought.
All right. Okay. Well, if you understand that, are you feeling fried, or should we keep going?
What about homework?
What about homework?
Or like, what about examples? Do we have that?
That's an example. We're not done with the introductory
Sure.
material.
Oh.
We still got to go on, talk about relations, talk about functions, and then we finally get to topological spaces. Good to keep going?
I have a G. I don't know what you do.
Other question. Is there anyone who's feeling burned out? Ready to stop? Good to keep going? Alright, let's keep going. Let's see. Dun, 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 dun. Okay, more definitions. This is one that we've already come across, so hopefully it will be pretty clear. Where is that? Definition 0. I guess none of you are following along in the book, so it doesn't matter what number it is. Definition: if we have two sets, then the set A minus B is equal to the set of all x such that what?
B is greater than, B is less than
It's
X
everything in A
is
that is
less
not
than
Yeah.
A.
It's a set of all
A.
B,
C.
B,
It's A. That
It's
is
a
not.
set of all.
B less than X
Integers.
less than A.
It's not integers.
It's everything in A that's not
Everything
B.
in A that's not a B, yeah.
It's a set of all x in A.
Bro, I was trying to be louder.
X is in A and not x is in B, or x is not in B. It's a set of all x such that x is in A and x is not in B.
Nice.
And x. Anyone confused by that definition? We have A, now remove everything that's in B. The set that remains is A minus B.
I don't know what Jake was saying.
He was thinking about numbers, I think. These are sets.
Yes.
Sets
Well, it's like-
A and B.
And then don't get more simplistic.
Okay. More notation. The cross product. The cross product, we've already gone over this, but let's make sure we got it. The cross product in of A and B is a set of all what?
Set of all.
X. Such that.
X comma Y gives us ordered pairs.
Mhm. Such that
X
X
is in A and Y
and Y
is
is
in
in
B.
B.
X is in A and Y is in B.
Discrete.
Discrete math.
This is exactly what we went over for this definition last week.
Yeah, well, you got pound at home 4 times to know.
Then watch the lectures 3 times after class.
For giving me sense.
Alright, so let's make sure we understand that. Let's do an example. A equal to the set 2, 4, 6. B equal to the set
Yeah.
1, 3, 5. Then A cross B is equal to the set of, we have 2 goes to 1, 2 goes to 3, 2, well,
4 goes to 3. Or like
2 goes to 5.
No, 4 does go to 3.
And then we have 3 or
Yup.
4 goes to 1, 4 goes to 3, 4 goes to 5, and then we have
6 goes to 1.
6 goes to 1, 6 goes to 3,
6 goes to
6 goes to 5. Oops. And then we end it. Notice how many elements are in A cross B?
9.
9. The size of A times the size of B. For each choice of our first element, A, we have 3 choices for how to finish it. 3 times 3, 9. Is this the same thing as B cross A?
No.
No, but you'll still get 9.
Yeah, B cross A would still give you the same amount of elements, but no. Now it's all backwards. We need 1 goes to 2, 3 goes to 2, 5 goes to 2, 1 goes to 4, 3 goes to 4, 5 goes to 4, 1 goes to 6, 3 goes to 6, 5 goes to 6. That would be B cross A. Does the order that I wrote these in matter
No.
when I did A cross B?
No.
No, because order doesn't matter in sets. The set x comma y is the same thing as the set y comma x. Right? Okay, that's the cross product. We did that. Cross product. In this context, I wanted to specify this right here is an ordered pair. This is not an interval of numbers.
Yeah.
Over here, we were talking about intervals of numbers. Over here now, this is an ordered pair with only 2 elements in it. Question, how many elements are in the interval 1 comma 2?
Infinity.
Infinite. This is infinite points when we're talking about an interval. There's only 2 elements in here when we're talking about ordered pair. They mean drastically different things. You have to know from context what's meant. So if you're ever confused by which of those we mean, ask, because very different. So I wanted to specify that. Okay, wanted to drive home cross product one more time to make sure we understand it. So what about if I have the sets A sub 1 cross A sub 2 cross A sub 3 cross ... cross A sub n. What is that going to give me?
What do you mean is what does that give you?
If I have n sets, column A sub 1, A sub 2, A sub 3, all the way to A sub n, then what is A sub 1 cross A sub 2 cross A sub 3 cross A sub 4 all the way up to cross A sub n? That's going to be the set of all n tuples. So x sub 1, x sub 2, x sub 3. Once again, we're getting dense notation.
Yes.
X sub n. So all these tuples
Paired with all the y.
such that x sub 1 is in A sub 1, and x sub 2 in A sub 2, and ... and x sub n in A sub n. Oops. Notice how similar this is to this.
Where's the y?
X sub 2 is our y now. It's just the name of a variable. I can use whatever I want, right?
Oh, yes.
Yes, sir. We good with that?
Yeah.
Let's see an example of this. What is R cross R give you? All the ordered pairs of real numbers. Or in other words, this gives you the plane that you're so used to. That's why when you're talking about a point in the plane, you use an ordered pair, x comma y.
Yo!
They call it the real number plane. It's the cross product of 2 real number lines. We call them real number lines because we think about them as one-dimensional. But the real numbers crossed with the real numbers just gives you the plane. Right? There's a one-to-one relationship between the real numbers and the real number line. Hence we call it the real number line. There's a one-to-one relation between R cross R and the plane. Same thing. So what then
cross it again.
R
No.
cross
No.
R
No.
cross R equal?
This is where our heads blow up.
It's just 3D space. You live in it. This is where you are. You hang out here all the time.
You are
So don't be
right
scared.
here.
R cross R cross. I should say that. Well, we'll get to manifolds eventually. For now, this is where you are.
Is this where we are? Triple R.
So we call this 3-dimensional Euclidean space. We call this 2-dimensional Euclidean space. And R just by itself, 1-dimensional Euclidean space. Not really, that implies a geometry. I shouldn't say that, sorry. But, yeah, you can think about 3-dimensional space as R cross R cross R. We can map it to this, right? And that's why when we talk about points in 3-dimensional space, we use 3 real numbers. Right?
Yeah.
Every point in space I can represent with 3 real numbers. And every 3 real numbers I can think of is a point in 3-dimensional space. Therefore, the two sets are equal. For every point in one set, a point in the other. So yeah, this is 3D space. And then we could easily talk about R cross R cross R cross R cross R cross R. We can do as many R's as we want. We can talk about as high dimensional space as we want. There's no limitation on how high of a dimensional space we can talk about.
Can we see that?
So even though it's really hard for us to imagine what 4-dimensional space looks like, doing math in 4-dimensional space is actually pretty straightforward.
Oh,
There's such thing as a 4-dimensional universe.
A 4-dimensional,
Universe.
okay.
sure, R's.
Yeah,
When you use 3 dimensions for space and 1 dimension for time, that's what general relativity uses to capture our universe.
That's right.
So it uses a 4-dimensional manifold to capture our universe.
That is right. You know time messes with how things work.
Time messes with how things work.
Is there even a time?
That is true.
Yes, there is time. Just like there is
How do we know?
space.
If you move fast,
Common misconception. Einstein's general theory of relativity tells us that time and space aren't real, they're imaginary. False.
Yeah,
He
that's
tells us that they're relative. The same way that my position is relative. You can say I'm at coordinates whatever you want.
how do you
Take
think
your coordinates
of that?
from you, take your
Who
coordinates from
thinks
you.
of that?
But there is still distances, and there
If you
is
move
still
fast through space,
What's
you
time?
literally time travel. Backwards.
Yeah.
what's time?
Time slows down. The faster you go,
It's one of
time
the
slows down.
dimensions we measure. Have I not done my special relativity lecture with you?
You've probably done it quite a while.
I did it last
You
year
did it with discrete, you didn't do it fast.
with discrete. Oh, you were in discrete. Remember we came to the physics classroom?
No.
He wasn't in discrete last year. He was in discrete 2 years.
Oh, you did. That's why you're so confusing. You did discrete 1 year, and then calculus the next year.
Are you
And
supposed to
Emma's
do
doing
that?
both of them right now. So I'm used to students doing it at the same time, and yeah, you're supposed to do both of them. The fact that you're not in calculus is a joke. You should be in it, unless it's during a required class.
Yeah, I couldn't.
Because
That makes sense.
Because then she'd have
Could
to
have
take
been.
chemistry, I was already
Yeah,
studying
why did-
speech, I had
why
to take
did
you
you
in
have
every.
you can take physics from me next year.
Emma's special. We're just
Oh,
like
wow.
doing
Deal with
math
Paul
and
later.
life.
God, get you.
What?
Yeah.
Yeah,
thought
She
you
has,
said-
you know what
she has a
meaning I can
one-on-one
apply.
M is not special.
No.
It's
So
going
I
up
had to
to
take a
fall
science class.
into-
Physics for me next
I
year.
did, and then Brother Him yelled at me.
What class are you gonna let go? Calculus?
It's because Emma.
I can be. I actually want to. I think what I'm going to do next year is do an applied calculus and physics. And those are 2 classes I teach. Sure.
Well, she got speech.
Remind me before I start so I can run
What's
past
her
on
science?
him, but he'll say yes. He's never said no to
Oh,
people doing that.
so she has her science and speech.
Botany.
Graduated people sitting in on my classes.
Oh.
Thanks for
Got
paying
your
my
hedges?
graduations.
Yeah, that's.
Well, that was Caitlin. She said it.
What?
And I trimmed butter and jerk.
Okay,
Yeah, they do that every year.
so cross products. Now, so hopefully with the talking about space, that helps bring home what these are, helps establish some intuition. Let's go over, write out a bunch of theorems, set theory, and then we can just prove whatever ones we want to prove. Maybe I'll just write them over here in the list. I don't think we'll need any of these until next week, so. I'll write them over here in the list, and then we can use the right-hand side of the board to just prove them.
This is more notation or what?
No, I'm going to write down a bunch of theorems that are true in set theory, and we can prove whichever of them that you want. And then when you feel like you've got a good handle on all of them, we'll move on to relations. Okay, so the first one, we're not going to bother with union is associative and commutative, and intersection is associative and commutative. Are we all good with that, or do we need explanations to what that is? We're all good with that? Okay, so then we'll move on to the more interesting ones. A intersect B union C, and a lot of you have seen this several times. It keeps coming up. This is equal to what?
B specific.
A.
C, A, N, A, B, R.
That was awful. All right. And we also have it the other way, right? A union B intersect C is equal to A union B intersect A union C. A cross B union C is equal to A cross B union A cross C.
We never proved that the cross product is distributed.
Okay. Same thing with the intersection. A cross B intersect C is equal to A cross B intersect A cross C. A cross B minus C is equal to A cross B minus A cross C. And these two are not intuitive in my brain, so I need to look at them while I write them. A minus B union C is equal to A minus B intersect A minus C. And then A minus B union C is equal to A minus B union A minus C. That seems odd. I wonder if I have those wrong. A minus C union.
You did say.
Okay. That's why. Okay, now it feels better. Okay. So these are all theorems from set theory that we will use 101 times in this class. So let's prove them. Or whichever ones you want to prove.
Well, I don't think we need to do we can do one
No,
or
we need
two,
to
but
We'll
we
call
don't
this
need to
one
do
1, 2, 3, 4, 5, 6, 7.
We don't need to do one or two. Let's do.
Well, no,
I
think
know,
we
I
need
want
to
to
do
see
Let's
one.
do
one or two, but not
Because I
both.
forgot
3 or
that.
4, but
Okay,
not both.
so let's start with 1.
Well, just show that and in orange order.
Right, it's just distributing and over or over and.
Yeah.
So let's do proof of 1. Let A and B be set such that, oh no, they're just sets. Okay, so then A intersect B union C, right?
Yeah.
This is equal to
The set.
the set, well we'll be more explicit. This is equal to A intersect, what's this? That's the set of all x such that x is in B or x is in C. What you have to remember when you're doing these types of proofs is that x is in B is a
Set.
no, x is in B. This whole thing is a
Fine.
or applies to what?
Both.
What can we use or
It's
on?
true.
It's true. So it's a,
Topology.
not tautology.
Proposition.
Proposition. We can only apply or to propositions. Or is an operator on propositions.
Oh.
X is in B is something that's true or false. It's not necessarily true. It's not necessarily false. But it is for sure true or false. So we have a proposition or a proposition. This whole thing here is a proposition. So when we use this notation, X such that something, some proposition, some predicate about X, when you plug in X into this thing, it gives you a proposition. If the proposition evaluates to true, we include the X. If the proposition evaluates, or the predicate evaluates to false, we don't include X. Understand exactly what we're using here and why we are using logic to talk about set theory. Remember, when you develop set theory, the only thing you already have is logic. So if we want to do set proofs in set theory, we have to fall back on logic. Right? So we need to get this thing back in terms of things we know how to talk about. We know how to talk about propositions and ORing propositions together. Good? Okay. Now this is equal to, okay, A intersected with some set. What does that give us? That gives us a set of all X such that X is in A and whatever this was. X is in B or X is in C. Now what do we have? We have a proposition and a proposition or a proposition. So we need to distribute an and across an or. This is going all the way back to our first lecture, and that is the same thing as a set of all X such that X is in A and X is in B, or X is in A and X is in C. Right? That's how you distribute an and across an or. Finally, going back to our set theory, how do we write this? This is a set of all X such that if X is in A and X is in B, that's X is in A intersect B. Or if X is in A and X is in C, that's X is in A intersect C. Right? And the set of all X such that X is in this or X is in this is the same thing as the set of all X, where X is, that's just A intersect B. You just union them together, is what I'm trying to say. Right?
Yeah.
What do we mean by this union this? We mean the set of all X such that X is in this or X is in this.
We define that.
That's our definition for what union means. Okay, so there's one example for proof 1. Any questions about that? Okay. Let's do another one. Pick another one.
3. Are we sure?
Huh?
I feel like 3 is better, so which one?
Well, what does cross mean?
3.
You do cross.
Okay.
Well, I'm saying is what would your symbol be? Wouldn't it be
Okay.
or it'd be
So we have A cross B union C. That's equal to the set of all X, Y such that X is in A and Y is in B union C. With me so far?
yeah.
Okay. That is equal to the set of all X, Y such that X is in A and Y is in B or Y is in C. Right? That's what it means for Y to be in B union C. It means Y is in B or Y is in C.
Right.
Now we're going to distribute our and across our or.
X is in B.
So it's a set of all X, Y such that distributing we get X in A and X in B.
And
or y in B, thank you, or x in A and y in C, right? And that is equal to, we kind of have to undo them both in one go.
I'm doing both in one go.
Yeah, I don't know another way to do it. We're just going to end up writing this, right? That's the same thing as A cross B union A cross C. Everything in this and all the set of ordered pairs where x is in A and y is in B, or all the set of ordered pairs where x is in A and y is in C. I guess I could have split this up into two. Here's how I should have done it. I just didn't want to write all the extra stuff, but we can. So this is the set of all x, y, such that x in A and y in B union the set of all x, y, such that x is in A and y is in C. And now we can use for definitions to say this is A cross B union A cross C. That's probably adds a helpful step. Good with that? Any questions about that?
Now we can do 5.
You good? You awake?
Mm-hmm.
5 is different than 6, bro.
Well, they're just the same. 5 is the same as 3.
Which one did we just do? 3?
Yeah.
Minus isn't the same as
Let's do
that.
6.
I'm wrong. She quits me out.
I hear a 6. Raise your hand if you want me to do 5. Nobody wants 5?
No, we don't like
6.
that number.
We already said that.
6
I know.
The
Just
whole
think
room yelled
I'm
6.
going to do 5 first if someone wanted to do 5, but no one wants to do 5. We can move on to 6.
6 sounds fine.
You don't get to monopolize the conversation about what we do and don't do.
Oh, Jake.
6.
What did he say?
Said you don't
All right.
realize what you do, don't you?
Yeah, it's literally what I'm gonna do.
All right, now I'm doing 5.
Oh no.
5. What's 5? This one. So now we're going
That's
to do
what I wanted.
A cross B minus C. All right. So this is equal to.
X such that X and Y.
Let's just write this one first. So we'll say this is A cross the set of all y such that y is in B and
No, y
y
is
is not in C, right?
Mm-hmm.
So then that's equal to, now when we cross with this, we have our ordered pairs. So this is all the xy such that x is in A and y is in B
Or
and
no, it's not.
y is not in C.
How do you get minus?
Yeah, so maybe this wasn't such a bad one to do. How do we continue?
I mean, you can continue and distribute the and, but how do you get a
How do
minus?
you distribute and over and?
You times it. Okay.
Get a bunch of minutes.
And.
Let's think about this. Let's reverse it and see if we can figure out where we're trying to go. You understand my plan?
Yeah.
So we're gonna have
That's 4.
A cross B, and we're doing 5, right?
Mm-hmm.
And we're gonna minus A cross C. What's that gonna be? That's going to be the set of all x, y such that
X is in A,
x is in A and
Y is in B.
y is in B,
Or,
and
oh, and y is not in.
not. We don't have a good way of handling it. If it's not in A cross C, that means it's not in A or it's not in C. X is not in A or B is not in C. Let me mess with the logic of this for a second. If x, y is not in A cross C, that means x, y is not in A and C. That means x, y is not in A or y is not in C. What's the good logic to do that?
Yeah.
Let's just try this way.
Whatever it said.
And x is not in A or y is not in C. Right?
He's not good.
Is that the correct interpretation of that?
You just said the opposite thing. Oh, no, that's B. X is in A and y is in B, or. And. Should that be an and between those two?
No. So if you're not in A cross C, then either x was not in A or y was not in C. So for example, let's think about the cross of 1 with 1.
Right.
X has to be 1 and y has to be 1. 1, 2 is not in the cross.
Yes.
So if this was an and, then that doesn't work. But if we have x not in A and y not in C, factor out the and. Let me write one more line between. A cross B minus A cross C. That is the set of all x, y such that x in A and y in B and not x in A and y in C. Right? And then when you distribute the not through, then it produces that. I think that's right.
How do you get that?
Yeah, so we have x in A and y in B.
Would you move the parentheses?
So let's think about this for a second. We can get x, y such that x in A, since these are all just and, we can write it however we want basically, and y in B.
Or.
Or y in X, or y, or
Oh, you
y
can't say
in
or,
C.
And we have y not in C,
Right, some converses.
and y not in C.
And parentheses.
So here's where the trick comes to this. Now I see it. You can or anything. We use this trick in logic. If I have x or anything, I could have only made it more true. I couldn't have made it more false.
Mm-hmm.
In other words, x or y is only true when x is also true. So by oring y, I couldn't have made this thing more false.
Right.
So it's still only true when it was true.
Right.
So we can OR onto this, or X not in A. We can OR something onto our expression, and we didn't give it more information. Right? If we knew that this was true, then we know that this is true. If we know that X is true, then we know that X or anything is true.
Right.
Does that make sense? So, feels weird that we would do that,
Well, it's because it's inclusive.
but the important part is you understand the logic on why we can do that. So this was a trick that we had to use in logic a couple times. And so, it makes sense that it's not obvious to you that, hey, we can do that.
Well, you already have it done.
Yeah, then we have it done because now we just change the order on these, right? And then we factor out the not, and then that's exactly what that is.
It's a good thing I was being sassy.
Yeah, it is a good thing you're being sassy. Okay, now we were going to do 7? 6?
6, but 6 is close to 7, so.
Seven
We've always
plus
done. Why is 6 right at 7?
Because 7, 8, 9.
Because it's bigger than that.
Mommy.
6. A minus B union C, okay, is equal to, we're going to skip all the way to just writing a set notation for the sake of not writing a bunch. So this is a set of all x such that x is in A and not maybe that's kind of weird to write.
And not.
And x, maybe we'll write it like this. X is not
B,
in
B or C.
B.
Or X is not in. No, just put the not on the outside.
And not just go straight to this. X in B or X in C. I wasn't going to leap quite that far in one go, but we'll go with it because it feels
That
weird
makes
finding a middle
no
ground.
sense to me.
Perfect
Just
sense.
jump right to that.
It doesn't make sense?
It does, that makes no sense.
Oh, it makes sense to you to jump right to that.
Yeah.
Okay. The reason it technically doesn't work is because we have to apply this before we apply this,
Oh, right.
right?
We are.
Stupid.
Well, I'm saying it is true, we didn't cheat, and we did maintain that that comes first, but we're using two definitions in one go. We're using the definition of this and this in one go. Anyways, if everyone's good with it, we'll continue. Okay, so now we're going to distribute the not, right? So that's a set of all x such that x in A and x is not in B and x is not in C. Did I do that right?
I think so.
Where are we trying to get? We're doing 6, right?
Yeah.
We want x is in A and x is not in B. Okay, so now we can rewrite this as x such that x is in A and
X is not
x
B.
is not in B.
When you do the same thing
And
with C.
X is in A. We can repeat it as many times as we want,
We just
right?
did it. That was
And-
cool, actually.
X is not in C. We can write x is in A and we can and it as many times as we want, right? If I have some expression x and y, that's definitely equal to x and y and x and x and x. We can and on as many x's as we want, and it doesn't change what this evaluates to.
Right.
Anding x is like multiplying by 1. Oring fault is like plusing 0.
Dude.
So are we good with this leap to this leap?
Yeah.
And then finally, just write down exactly what it says. That is A minus B union, or intersect A. And then for the union, I imagine that we're gonna have to do a similar thing where we just,
Change your ands to ors besides that middle guy.
well, I think we're gonna have to add a or whatever we want because it's still true.
Alright.
So, because we're gonna need to add one more.
Yeah, it's probably gonna be ends.
Okay. We good with all those, you think?
Well,
Okay. Well, I can't stand anymore, so we'll call it there.